Swayam Prabha. Digital India. Educated India.
Welcome back to our second lecture on Introduction to Aerodynamics. And as you can see, I am going a bit slow. I think this whole first week lectures will be in an introductory manner. Today I am going to talk about the course content a bit. Again, I would so you at least have some idea of what to expect in this course. I will go over course content, and in that while I talk about the content in the course, I will talk about a little bit of these concepts, so that you have some idea about what these things are. Okay, so first of all, terminology and scope. Now, this one I do not need to really elaborate. We will go over the terminologies as and when they arrive. So, although I have put it as at number 1, it essentially just talks about the introductory phase of our presentation. After that, we will take a quick look. So, not detailed look, but a quick look at how lift is generated, how drag is generated, and of course, if you have distributed loads, then by taking an axis around which you want to calculate moments. So, if you remember your courses from statics and dynamics in high school or in first year, I think if you have a distributed load, so lift and drag, these are distributed loads on the wings and the fuselage and the control surfaces and the the vertical tail, horizontal tail, etc. So, if you use the moment arm, so the force, if you use the moment arm about a certain point, you can get the moments due to this lift and drag forces. You will see that when aircrafts need to maneuver or change angle of attack or rotate during takeoff, some of these moments are necessary. Some of these moments are necessary to achieve desired attitude, and so there are lift and drag are two well defined forces. Lift is something that is okay. Let me quickly show how lift is defined. Suppose this is your aircraft. Sorry. Okay, actually I might have the diagram in some of the follow up slides. Okay. So, talking about lift and drag. So, what happens is when your aircraft is flying, let me get a better picture. Okay. So, lift and drag. Okay. So, what happens is, if you look at this picture in detail, so we have the side view of an aircraft, as you see here. This is known as the vertical tail. This is known as the horizontal tail. This small portion that you see here can be deflected. It is known as the rudder, and this portion can also be deflected. It is known as the elevator. Now, in some aircrafts, this whole thing can be deflected. So, those are essentially you will see the purpose of these deflections. Although you can see that these the horizontal tail also has the shape of what we have on the main wing, and the horizontal tail will also produce some lift force. The primary lifting force that keeps the aircraft afloat, helps the aircraft fight gravity or do the maneuvers, really comes from the main wing. Okay. Although there are small moments that lift and drag forces generated by these control surfaces, I mean this one will not generate lift force, but this one will generate a small amount of lift force, and in some cases it will be actually directed downwards rather upwards, but nonetheless the purpose of these surfaces is really to provide moments. So, if you think of if this is the center of gravity of the aircraft and you can think of a coordinate system. Now, there can be different coordinate systems that you can use to your advantage. In this case, through the center of gravity, I am using a vertical and horizontal coordinate system. Sometimes it might be convenient to use a coordinate system that is aligned with the relative wind. So, you see this is the relative wind. What does relative wind mean? Relative wind means that when the aircraft is moving with a velocity, it is seeing air come towards it at a certain velocity, magnitude and direction. So, that is the relative wind. Now, the relative wind is really a combination of the negative of the vehicle speed plus the ambient velocity in atmosphere at that location. But for all practical purposes the speed of these vehicles are much higher than the ambient velocities that might exist in atmosphere. So, for most practical purposes unless you are explicitly given that some high velocity wind motion is happening in the vicinity of the aircraft, in that case you have to use a superposition, but in most cases you can just use the negative of the velocity of the vehicle as the relative wind. So, you can ignore the small velocity of wind that is in the ambient, because the velocity of the vehicle is sometimes orders of magnitude larger than the fluctuations in velocity in the ambient atmosphere. So, if you think of so this is your relative wind. In this particular case my relative wind is aligning with the horizontal. It is not necessary that they align like that. It is just something that has happened at this point, and this is a case of, well, this can be a case of straight and level flight. That is, your vehicle is headed along the horizontal direction. So, the path of your vehicle. So, we have this thing called, just a second. Okay, so, this one, if you see, there is something called the flight path angle, that is the angle between the relative wind and the horizontal. Okay, the relative wind is nothing but the negative of the velocity of the vehicle. As I said, the fluctuations in the ambient velocity are often negligible compared to the velocity of the vehicle, and hence the negative of the velocity of the vehicle can be used as the relative wind velocity vector in magnitude and direction both. So, you have to take the negative of the velocity vector of the aircraft. Now, if you draw the horizontal, then the angle between the relative wind and the horizontal is defined as the flight path angle. If you see, the weight of the aircraft is acting vertically downwards. This is always going to be vertically downwards to the center of the earth, right. On the other hand, you see that my lift force is now tilted. So, why is my lift force tilted like that? Because when air is flowing, so in this case okay, let me first talk about the angles, because once I draw the streamlines, the angles will get a little difficult to see. Now, the angle between the relative wind and the horizontal is my flight path angle, okay, that is gamma. You can see that here also my flight path angle is showing up, and here also my flight path angle is showing up. And the reason is, when air is flowing over the wing, so you have the wing, at this point let me draw the chord line. Okay, let me just draw it here. So, okay, if you see this is the wing, and if you join the trailing edge of the wing with the leading edge of the wing, this red dotted line is the chord of the wing, okay, and I have extended it all the way and I have called it the chord line. Okay. Sometimes it might be a bit tricky to find the chord of an airfoil, because here my airfoil is quite a simple looking airfoil. This is your chord joining the leading edge with the trailing edge. Airfoils can be symmetric, airfoils can be cambered. We will talk about those things, but right now just in a manner to indicate the existence of those things without going into detail. So, an airfoil like this can be considered as symmetric. The drawing is not, let me okay. Let us assume so airfoils can be symmetric or airfoils can be asymmetric. Okay, we will come back to the airfoil at a later point. I am having a little bit of difficulty in drawing a symmetric airfoil on this setup. So, at this point let us see that this is the chord line. So, that is what the chord line . Okay, I think I have gone to the present view. So, the angle between the chord line and the relative wind is known as the angle of attack. So, the angle between the horizontal and the relative wind is known as the flight path angle, and the angle between the chord line and the relative wind is known as the angle of attack. In this particular case, you see that the thrust vector is not aligned with the relative wind direction. In many cases, you will see that the thrust from the engine, the thrust vector, thrust is a force. So, thrust will have a direction. In this particular case, you see that the thrust vector makes an angle alpha t, alpha thrust with the relative wind. In terms of the forces, we have the weight which acts vertically. So, if this is the horizontal line, then of course, this is 90 degrees. So, then this is the vertical line and the weight acts along that. Now, you see that the lift is not a vertical force. Okay. In some places, and I have seen something that you would find on of course, this is just a matter of definition, but nonetheless, so that all of you stay on the same page when you talk about what you are talking about, some of these definitions are important, and the way lift is defined is it is the component of the resultant force that is perpendicular to the relative wind direction. Okay. So, it is not the horizontal force on the aircraft. Under some circumstances, sorry, it is not the vertical force on the aircraft. So, weight is always the vertical force, okay, directed towards downwards, directed towards the center of the earth, but the lift force is not a vertically upward force. Some textbooks or some web resources have confusing things about this particular aspect. So, lift is the resolution of the force. So, now by now I think the angles are clear. So, flight path angle is the angle between the relative wind direction and the horizontal direction. The angle of attack is the angle between the chord line of the airfoil and the relative wind direction. The thrust vector angle, as I said, alpha t is between the thrust vector and the relative wind direction. So, all these you can see are with respect to the relative wind direction. Okay. Flight path angle is from relative wind to the horizontal, angle of attack is from relative wind to the chord line, and the thrust vector angle is from the relative wind to the direction of the thrust vector. So, all these angles are defined with respect to the relative wind, and now when air is flowing over the airfoil. So, if I now draw, now that we are done with the angles. So, if when air is flowing over the top surface, sorry, you cannot have an intersection like that, because here the particles are, it's okay. We will see under what conditions, for example, streamlines cannot intersect, but path lines can intersect, okay. And so we will see those things at a later point. Okay, anyway, so just think of these as streamlines in a steady flow, or at least at that point of time. You will see that streamlines in an unsteady flow and streamlines in a steady flow have some nuances that you have to keep in mind. When it is a steady flow, a lot of these lines become similar. In unsteady flow, they have some dissimilarity. So, we will talk about that thing later, but now at this point think of air going over the airfoil and air going below the airfoil. Now, we will see that during this the motion of air over and below the airfoil, the velocity of air on the top surface on the average is higher than the velocity of air on the bottom surface on the average. So, what happens is if you model it as sometimes you can model it using the Bernoulli's theorem, which essentially is some P naught is equal to P plus half rho u square. If your u goes up, your pressure goes down. So, since all these streamlines started from the same P naught, and if the velocity here is higher lower than the velocity here on the average, then the pressure on the top surface will be lower than the pressure on the bottom surface on the average. Okay. So, these things will vary from point to point. So, on the top surface of the wing, velocity will vary from point to point, hence pressure will vary from point to point. Similarly, on the bottom surface, velocity will vary from location to location, and hence pressure will also vary from location to location, but on the average pressure on the lower surface will be higher than pressure on the upper surface. As a result of this, because of this distribution of pressure. So, if you think of an airfoil over which you have air passing, okay. So, we have air flowing over an airfoil, and for some special reason the velocity on the top surface on the average is more than the velocity on the bottom surface. So, that kind of controls or influences the pressure distribution on the surface of this wing. Now, there are two kinds of forces that are developed on the wing. One is the normal force due to pressure, and the other is something known as the shear force. Shear force is due to viscosity. So, if you draw, so you have air. So, this think of it as a cross section of the wing at a certain location. Okay. So, you have a wing going all the way from the fuselage to the wing tips and you have taken a cross section somewhere in between, and you are looking at air flowing on the top of the airfoil, at bottom of the airfoil, and you are trying to figure out what is the force on this airfoil section. Now, the source of force on the airfoil section is really from two kinds. One is, so if you think of molecules of air sweeping past the top surface. So, while they are sweeping past the top surface, the molecules are colliding with each other and also colliding with the surface of the airfoil, and that leads to the generation of a normal force. And we will see that the magnitude of, so the force is locally perpendicular to the surface, but the magnitude of this force will change from location to location. It will actually be high in the, sorry, it is not normal. Let me remove this one. Okay, so okay, so what will happen is it will be normal. I do not know why that is happening, but and then for reasons we will discuss, the pressure will decrease here and then again increase. On the other hand, on the lower part, pressure will decrease and increase again, but the pressure on the bottom surface on the average will remain higher than the pressure on the top surface. So, what that will do is, if you integrate the effect of these forces, what you will find is there is a lifting behavior that will come in. Okay. So, lower portion of the wing has higher force, upper portion of the wing has the lesser force. So, the resultant of this normal distribution will act through a point which you can think of as the center of pressure. Similarly, there is another source of force which arises because of the viscosity of the fluid, and that force is directed in a tangential manner. You see it is almost on the surface of the airfoil. So, that is given the notation tau wall, and it means shear force or shear stress, force per unit area, shear force at the wall. Now, why this shear force happens? This you understand why the normal force happens. It is just because of the effect of pressure, and pressure is really because of the bombardment of the molecules. And per Bernoulli's theorem, where velocity is more, your pressure is less, where velocity is less, your pressure is more. And since these streamlines are starting from the same location, you can say that the pressure here is less than the pressure here on the average. So, distribution like this is feasible. On the other hand, shear force at the wall is due to viscous effects. So, what happens is, since air has viscosity, and if you zoom in, say I am zooming into a small portion of this airfoil. So, I am zooming in. So, that is my airfoil surface, and flow is going past the airfoil. What happens is, at the wall of the airfoil, due to adhesion and due to viscosity, the particle of air that is touching the surface will have 0 velocity. So, this is something before this idea was invented or discovered by Prandtl, people were had this open ended situation of the D'Alembert's paradox, and we will talk about it at some point. But Prandtl found out or established on a theoretical basis that when you have a flow like this near a surface and the flow has viscosity, what will happen is the particles close to the wall will stick to it and stop moving, and they will try to exert through viscosity an effect on the neighboring particles to slow down as well. The particles here, so the particles here will slow down, these guys will exert a slowing down behavior on the next one. So, that way a velocity distribution is created. So, if you zoom in to this very near the wall, okay. So, boundary layer thickness. So, this is called a boundary layer. Now, this is one of the very important concepts in fluid mechanics or aerodynamics. Boundary layer is, if you go near the wall, your velocity gets into something called the no slip behavior. That is, there is no relative velocity between this particle and the wall. Okay. So, the particle sticks to the wall and it does not move with respect to the wall. So, its horizontal velocity component or velocity component parallel to the wall, of course, normal to the wall, it is not a porous wall here. So, normal component is 0 and the tangential component of velocity parallel to the wall also becomes 0 at the wall. As you go away from the wall towards the free stream, suppose the free stream velocity is u infinity. So, beyond this you almost become u infinity. I say almost because it does it asymptotically. Okay. So, it goes from 0 to u infinity. So, it goes from 0 velocity. So, you can think of these horizontal line magnitudes as the magnitude of velocity, and eventually you reach u infinity magnitude asymptotically. Okay. So, it takes forever, but what we do is we say that the distance that is required to reach about 95% of u infinity. In some texts I also see 99%, but nonetheless it is just a convention. So, essentially velocity goes from 0, keeps on increasing to the free stream value, but it takes forever because it reaches the free stream value asymptotically. But so, we define boundary layer thickness as that distance where the velocity has gone up to 95% of the free stream velocity. So, if this is delta, then u here is 0.95 times u infinity. Okay. So, that is how we define boundary layer, and in the boundary layer you see there is a velocity gradient. Your u is 0 here and u goes to u infinity here. It can be shown that the wall shear stress is given as okay. So, the rate at which u is changing in the wall normal direction at the wall. Okay. You have to calculate the gradient at the wall, because you see that your du d eta is changing as you move away from the wall. Okay. So, if you want to find the shear stress at the wall, you have to first know the viscosity of the fluid and then multiply it with the velocity gradient at the location where you are seeking the viscosity. In this case, we are seeking the shear stress at the wall point. So, you can use this relationship. So, that way if you run this thing at every point, you can find the shear stress at each of these locations. So, here you have a distributed normal force, here you have a distributed shear force over the airfoil surface. So, if you create the resultant force, it will look something like So, this is where lift and drag are actually perpendicular to each other. So, the resultant force due to that distributed lift and due to distributed normal force and due to the distributed. So, this is distributed normal force, you can put an S. So, S you can think of starting from the front stagnation point, you have a wall fitted coordinate system S, and normal force as a function of S. Similarly, if you start from here and you define a coordinate like that, you can also say wall shear force as a function of S. Using these two distributions, you find the resultant force acting on the airfoil cross section, and that is R. Then what you do is you resolve R into a force perpendicular to V infinity. So, that is your lift force. You resolve R into a force along the relative wind direction, that is your drag force. Okay. So, keep in mind that your the lift force and the drag force are given with respect to the relative wind direction. So, you find the resultant force due to the normal force and the shear force distribution, you find the resultant force R, then you take the component of that resultant force in a direction perpendicular to the velocity relative velocity direction, that gives you lift, and you take it along the relative wind direction, that gives you drag. And for efficient aerodynamic design, your lift should be significantly greater than drag. Remember, in the previous class I talked about this thing from Karamchetty, where he poses the question, what is a wing? Of course, this is pretty much what most of us will think is a wing, that is mounted on the aircraft on the sides, but Karamchetty says that essentially anything that when properly oriented not just generates lift which is significantly greater than the drag is a wing. So, in this case you have a resultant force R, and when you take the components of lift and drag, so components of R along those two directions, which are one normal to the velocity relative velocity and the other along the relative velocity, you find lift and drag, and then you see whether lift is significantly greater than drag. In this case, of course, aircrafts are designed in such a way that lift is significantly greater than drag. So, I think that thing will be satisfied. But another thing of importance is when you have a distributed force on an extended structure, you can create a resultant force like R in this case, but if you keep on shifting the resultant force, your resultant force is really at the center of pressure. So, if you shift the force, some moment has to be accounted for as well. So, we will talk about how the resultant force R acting through the center of pressure can be shifted to other points, and how the equivalent moment has to be brought in about the points around which you are trying to get the equivalent force and moments. So, we will come to that at a later point. At this point, we are focused on the resultant force R and its component in the direction perpendicular and along the relative wind direction, and that is your lift and drag. Okay, so, drag, you understand, it comes it comes as a component of the resultant force along the direction of your relative wind, and you will see that a big chunk of drag actually comes from the shear force distribution, and the majority of lift comes from the normal force distribution. Okay. As you can pretty much see that the the shear forces are directed in such a way that their contribution to the lift force may not be significant, but again you cannot really say all these things upfront. You can speculate, you can make a reasonable guess, but you really have to work it out. You have to work it out, get the resultant force. and then see what kind of components you get. The boundary layer concept, I would once again you have already, I have talked about the link of those videos. So, this is the page from the HML. So, remember I gave you the list of the link where you can find those extraordinary videos about fluid mechanics. So, there you can go through boundary layer. Okay, it is not boundary layer control. Okay, this one you see here, it says fundamentals of boundary layers. So, to understand this concept of shear stress that acts on like that airfoil cross section we were considering, you have to understand aspects of the boundary layer. So, it will be really good at this point if you take a look at this video, once you are done with this, once you watch this lecture, then you go and watch this video on NCFMF, and then you will understand that depending on the nature of the boundary layer, to begin with, you understand that the the relative velocity has come to 0. So, it is called the no slip condition, okay, and no slip can be for velocity and for temperature as well. Okay. So, there is a parameter called Knudsen number, and depending on the range of that Knudsen number, your flow at the wall can actually behave. So, there are things like slip, no slip, etc. So, Knudsen number is defined as mean free path divided by a characteristic dimension of, say, of a vehicle or a wing, etc. Now, the mean free path is the average distance the molecules have to travel before they collide with each other. So, it is not a fixed number, sometimes they can collide just within a short distance, sometimes they have to travel longer to collide. So, if you take a statistical average, you can figure out what is the average distance these molecules have to travel to collide with each other. Now, this distance is really small. So, when you divide it by L, characteristic dimension, then Knudsen number becomes a really small number, and a very small Knudsen number is characteristic of continuum flow, which means that given the size of your body, the molecules are almost like packed together. Okay. The distance they are traveling to hit each other is really small compared to L. But if you go up in the atmosphere, I think I mentioned this thing at some point in the last lecture, that as you go in altitude, atmosphere becomes rarer, density becomes less, and there comes a point where rarefied gas dynamic effects start showing up. In those conditions, depending on the Knudsen number, you can actually start seeing velocity slip and temperature slip. But for most of our applications, so that happens at really high altitudes, and those kind of situations happen in re-entry vehicles. Say the Apollo re-entry, lunar re-entry, or even the space shuttle re-entry. I have to look it up, but it depends on the altitude. As I said in the last class, that powered flight. So, if you have an air breathing engine, because you have to because you need a certain kind of density of the ambient air to even generate thrust, you cannot really go that high where you are having Knudsen number falling in this range where you have like slip conditions. So, re-entry vehicles, you can have, actually you can not only have slip, you can also have situations where you have to discard Navier-Stokes completely, and you have to use some kind of molecular collision simulations to find the forces and etc. on the vehicle. So, if you are coming back from orbit or so outer, not from the ground, but if you are coming from outside, then you will kind of hit all these ranges of Knudsen number. And just so that you guys have at least some starting idea about this. So, whenever I say these things, just go and look it up on Wikipedia. So, fundamentals of boundary layer, watch it, and you will get a physical feel of what this shear force on the wing is all about. And then now I said that the velocity of the particle at the wall becomes 0, but there is a little nuance to that. And just like Mach number, remember, gives you the range of where compressible flow occurs, where supersonic flow occurs, where hypersonic flow occurs, where transonic behavior occurs. So, Mach number gives you an indication to all those behavior. Knudsen number gives you where you should use free molecular flow as your governing equation for your governing fluid behavior, where you can use Navier-Stokes with slip conditions. So, Navier-Stokes is essentially the governing equation for fluid, for viscous fluid flow. And if you think that you will always have that no slip condition, in all of your aircraft wings you will have no slip conditions, there is no slip, neither velocity slip nor temperature slip. But what I am saying is, if you are re-entering from orbit, you might hit very rare portions of the atmosphere where the mean free paths are large enough, and what can happen is you have these two important ranges. Okay, remember that for the compressible behavior we had Mach number of 0.3. So, here remember that there is a number of a Knudsen number of 0.03, below which in this region your no slip behavior is what happens. Okay, so, for your aircraft wing that we drew, the Knudsen number is far below 0.03, you can work it out, okay, because that lambda, say altitudes at 32,000 feet is really small. So, it will be far on the left of this limit. But again, as it is more about the re-entry vehicle, as the re-entry vehicle comes to a certain altitude where the lambda by L hits 0.03, on the left hand side here you can use Navier-Stokes with, so read up Knudsen number, at least you will not maybe the mathematical basis of these things, but at least you will know on a qualitative fashion what is this Knudsen number and why you can use Navier-Stokes with no slip condition. If it is below 0.03. On the other hand, up to Knudsen number of 0.2 in this region you can use Navier-Stokes with slip conditions, with velocity and temperature slip. What this means is, velocity of a particle at the wall does not need to be 0, okay, with relative to the wall. However, if you are at a Knudsen number higher than 0.2, you cannot use Navier-Stokes anymore. Oh, this cannot be seen. Okay, you can Navier-Stokes cannot be used, and here you have to use something called free molecular simulation. This is free molecular flow. However, I should also point out that you would never reach that extreme if you are talking about surface to air vehicles that ply between surface air back to surface, because the surface to air and back to surface vehicles, because of their engine operation, they cannot go to such extreme heights, because you will see that the dynamic pressure, there is something which we in advanced gas dynamics or advanced hypersonics, not advanced hypersonics, but in hypersonics, you talk about these things that of the constant dynamic pressure trajectory of vehicles, and you will see that your vehicle cannot fly if you fly below a certain dynamic pressure trajectory, or if you fly below a certain dynamic pressure, then your engines will not be able to produce enough thrust, your lifting surfaces will not be able to produce enough lift. So, you cannot really go arbitrarily high. So, given that limitation, your Knudsen number will never reach these slip conditions, and forget reaching the free molecular situation. But if you have re-entry vehicles, that is coming from almost near vacuum or maybe vacuum back into the atmosphere, they hit all these regimes, and you need to account for the pressure distribution, the force distribution on these vehicles by using this suitable set of equations. Okay. You cannot just run the conventional approach that we would do for the aircrafts flying at 32,000 feet or even 85,000 feet. I think as high as 200,000 feet, your mean free path is about 10 to the power minus 3 feet, which gives a Knudsen number of 10 to the power minus 5. So, even at a height of like 200,000 feet, the SR-71 Blackbird that I showed in the first slide can fly up to it, can fly at 85,000. I am sure it can fly even higher than that. In aircraft performance, you learn about these expressions such as the service ceiling of an aircraft, the absolute ceiling of an aircraft. It is not exactly in the jurisdiction of aerodynamics, at least in terms of curriculum, but nonetheless your rate of climb. So, I think the service ceiling, so absolute ceiling is when you do not have excess power. So, you need the engine will produce some power. So, power available, and then you will have a power required, and the difference can help you in your rate of climb, but at some point it can so happen that you do not have any excess power left. So, you cannot have any rate of climb, and that is your absolute ceiling. On the other hand, just below the absolute ceiling, we define another height where your maximum rate of climb is 100 feet per minute or something. I may not be exactly correct on these numbers, but so it's a agreed upon rate of maximum rate of climb. So, it is about to hit the absolute ceiling, is called the service ceiling. So, I am saying that the absolute ceiling of all these aircrafts that you will be dealing with, or we will be dealing with, will never hit the Knudsen number range where you have to consider the no slip, the slip conditions, forget the molecular. So, most of it will be no slip Navier-Stokes, and when you have the no slip, you have what we just discussed, you have this profile. Okay. So, no slip means the velocity of a air particle near the wall will become 0 with respect to the wall, no slip. That is what is meant by no slip, and it is because of viscosity. Now, let me go back to where we started all this discussion from. So, now you have some idea about lift and drag, okay, the component normal to the relative wind, the component along the relative wind, lift and drag, and moments we will look at moments, but at this point you can sense that if you have a distributed load and you consider say an axis through the center of gravity, you can figure out what is the moment of all these forces around that axis going through the center of gravity. Okay. So, that is in some sense what we mean by the moment generated by this force distributed load. While we talk about the moments on a wing, you will see the importance of some locations around which we take the moments. So, when we look at the entire aircraft, we really focus on the center of gravity, and all these moments etcetera we take with respect to the center of gravity of the aircraft. But when you are testing a wing section, sometimes we look at moments with respect to the leading edge. Okay. So, your resultant force R for the wing cross section is going through the center of pressure of the wing cross section. There is no moment, just the resultant force. Now, you might like to find what is the moment around the leading edge, what is the moment around the quarter chord location, and we will talk about why these things are important. Okay? Quarter chord location, and there is something called the aerodynamic center of the wing cross section. For thin airfoils, we will see that the aerodynamic center is located at the quarter chord. Okay? And then for thin symmetric, thin cambered, we will see that the center of pressure for the thin symmetric lies also on the quarter chord point. On the other hand, for the thin cambered, the center of pressure may be somewhere else. For a generic airfoil which is not thin, so it can be thick cambered, etc., the aerodynamic center also may not be located exactly at the quarter chord, and center of pressure of course can be anywhere. So, when we look at the moments that are generated on a airfoil or a wing cross section, we are often interested to look at these things around these locations: leading edge, quarter chord, aerodynamic center, center of pressure. Center of pressure, of course, you do not have any moment, because that is only the the resultant force acts through that point with no moment around that point. And as I said, that when you look at the entire vehicle, then you really look at an axis through the center of gravity of the entire aircraft. But when you look at individual components, the wing, the airfoil of the wing, then you have some of these important locations around which you want to consider the moment. So, this is the leading edge. So, you might like to find moment about the leading edge. If you think that this is your chord, then you have, say, half chord, quarter chord. So, you might like to find moment about quarter chord. Your aerodynamic center, is of course, is not a thin airfoil, but if you assume that it is somehow near the quarter chord, so that is your aerodynamic center location, and center of pressure is where the resultant force is acting. Now, why this aerodynamic center is important is the moment about this aerodynamic center is independent of the angle of attack. Now, this is I think very counterintuitive or non-intuitive. So, moment about the aerodynamic center is actually constant with angle of attack. So, okay, so aerodynamic center has this special property that moment about the aerodynamic center with respect to angle of attack, the the dou moment about aerodynamic center with respect to angle of attack is 0. And we will see these things, there are at least for the thin airfoil theory, we can show some of these things. So, again, this is just a quick introduction to these things. Okay, we will go in at length with each of these things, because how lift is generated is a very there is a very strong analytical foundation to how lift is generated, because a lot of these kind of wings and the math around it was developed before the computers came in, and the first departments of aeronautics came up in MIT and University of Michigan as early as 1916. So, in those period of time, a lot of mathematicians actually were exploring the problems of lift, etc. So, you will see that this has a very strong mathematical foundation. Okay. So, when we do lift, we will go at we have to go in quite a bit of depth. We will learn what is potential flow, how you can superpose different potential flows to get a complex flow field, then how lift can be the circulation theory, starting vortex, bound vortex, then we will. So, essentially, but I have pushed that one a little later in the semester. because it has a little bit of complicated mathematics, which some students feel they lose their interest in aerodynamics when they see the rigor of Zukowski transformation. But again I will try to introduce you these things to you in a little easy to understand way, I guess. So, lift, drag and moments, aircraft components and their functions. So, you need to have some literacy in aircraft components and the way they function. So, we will actually first get into the physics of drag. You already saw how drag is generated. You have a pressure normal force distribution, shear force distribution, you integrate them, get R, resolve along the velocity, relative wind. But the physics of drag really has a lot of interesting aspects of aerodynamics that if you learn by using drag as an excuse, then a lot of theoretical things about fluid mechanics will start becoming evident. And then we also have flow over. So, after the drag and the boundary layer basics, we find we look at what is skin friction drag, what is separation drag. So, skin friction drag is really due to the shear stresses, but what is this new kind of drag, flow separation drag, and I have not added here. We will also learn about wave drag. Okay, so, in the next class we will still continue with this course content, because this is a good time where we can like introduce topics that you can at least look up here and there and get prepared for the detailed treatment of this subject matter. And these are the related courses that you can see. I have written some of these related courses that you can find in subsequent semesters. I have already talked about this in the previous class, but it is just listed here for your reference. Okay, so I think we will end our discussion for this class here. Thank you for your attention, and we will continue in the next session.